and today we'll be talking about related functions. And that's a pretty broad topic, but what I mean with related functions is functions that share the same variables or connected variables that, for example, can be derived from each other and that give different outcomes. So, for example, in a sphere, the variable for the volume, the variable for the surface area is radius, but they give different outcomes. They give the volume and their surface area. But like for the same sphere, the diameter can be used to find the radius. So those are two like interconnected variables that can be used for the same outcome. So for example, say you have f of x is equal to blah blah blah, and then g of x is equal to blah blah blah. You can rewrite the function of f as a function of g, right? So a bit like a composite function. So why do we need that? Well, it lets us get the value that we're searching for based on different variables that we know. We don't always know x. We might know f of x as a whole. So when you have g of f, that saves you the process from going from x to f of x to g. Sometimes you just don't know all of the variables. And when you get these equations, you're way more efficient at finding your needed answer. So the way that we can learn this is by basically just doing examples. So let's look at our first examples where we have different functions of properties of a square, right? Here, this is the perimeter, this is the area, and this is the volume of a cube. This is the area of one side, this is the perimeter of one side of the cube, and then this is the whole cube as a whole, right? So our purpose for this task is to express the perimeter in terms of the area, to express the volume in terms of the perimeter, and to express the area in terms of the volume, right? And I suggest you do this by yourself. If you think you have an idea, just go try it out, and then you come back. But if not, then you can just watch me do this first example. Now, what I think your strategy should be is to rearrange for the common variable. Now, there's other ways you can do it. You can just think logically about what I need to do to get from A to get to P, right? What do I have to do? What are the processes, right? And that's fine, but when the equation gets a bit more complicated, this is the way to go, in my opinion. It's way easier and it's clearer. You're less likely to make a mistake. Alright, so let's look at what can be done. So let's express s in terms of the outcome that we get. So for example, here s is equals to 1/4 p, right? And you don't have to rewrite p of s because you know it's a function. Well, in this case, we're using it as a function. Here, s is the square root of area, and then here, s is the cubed root of volume, right? All of that makes sense. So our first task was to find perimeter in terms of area, right? Now, what is perimeter? Well, perimeter in terms of s, that's 4s, right? But now we don't have s. We need to have a, right? But that's exactly why we found s in terms of a, right? So now we know that s is equal to the square root of a, right? We figured it out right here. And what we can do now is we can just plug in this for s, right? So we know that this would be equal 4 square root a. So b in terms of a would be 4 root a, right? That's our first answer. I hope that makes sense. Let's look at our second question. Our second question was about expressing volume in terms of perimeter, right? And what is volume by itself? Well, volume by itself is s squared, and s, as we figured out here, is 1/4 perimeter, right? Volume is s cubed. I'm pretty sure I said s squared a couple of seconds ago, but it's s cubed. And what we do is we input the perimeter for the s. So volume in terms of perimeter is equals to 1/4 perimeter cubed, which is 1/64 perimeter cubed. And for our last one, where we're going to express area in terms of volume, we're going to once again look back and think, what is S in terms of volume, right? Well, S is equal to the cubed root of volume, right? And A, that's just S squared, right? So what we have, A of V is cubed root V squared, right? Because this is S. You have A equals S squared. Your S turns into this. And you can simplify this to A of V is equal to V to the power of 2/3. Right? And these are our functions. They're like composite functions, but we just rewrite them in terms of V or P or A. So now, say you want to find the volume of a cube, right? But you don't know its side length. You know its perimeter, right? And instead of doing this whole process every single time, you create a generalized formula. That's all we're doing. It's a pretty logical procedure if you think about it, but we're just putting it into a generalized formula. Let's look at a second example. Alright, so this is our second and final example where we're looking at a sphere, right? And the properties of a sphere. And here, look, they're all expressed in radius, right? So this is their common variable. They're all using radius to get the final answer. And here we have the formula for the cross section of the sphere. Here we have the surface area of the sphere. And here we have the volume of the sphere, right? And our task this time is to express the cross-sectional area in terms of the volume, the surface area in terms of the cross-sectional area, and the volume in terms of the surface area, right? This is what we're trying to find. I encourage you to go do this yourself because you're familiar now. You saw the last example. Do the same procedure, see if you're right, and then come back. This one is a bit more complex algebraically wise, but it's the same concept. Alright, so once again, we're going to do the same thing and we're going to express radius in terms of the outcomes. So for example, in here, in terms of the cross-sectional area. So here, our radius would be, well, we divide area by pi, and then we take the square root of that. So it would be area over pi, all of that square rooted, right? Then over here, what would S surface area be? Well, that would be, think about it, you're dividing surface area by 4 pi, and then you're square rooting that. Right? And then last but not least, what is radius in terms of volume? Well, you're dividing the volume by 3/4, so you have 4 volume over 3, and then you're also dividing it by pi, and then you're cube rooting that. So what that gets us is the cubed root of 4v over 3 pi, and to make this a bit cleaner, I would just write it 4v over 3 pi to the power of 1/3, so you don't have to draw the root sign every time, but makes no difference. Alright, so what is our first task over here? Well, our first function is area in terms of volume, right? We know that area is equal to pi r squared, and we also know that r in terms of volume, because that's what we're looking for, is equals to 4v 3 pi to 1/3, right? So we just plug this whole thing in instead of the r right here. So what do we get? Well, we get area in terms of volume is equals to pi 4v over 3 pi 1/3 to the 1/3, all of that squared. So our final answer in terms of volume would be pi times 4 times volume over 3 pi to the power of 2 over 3, right? That's our first function that we've expressed. This is the answer. All right, let's look at our second one. Our second one is really simple. Think about it. We're expressing, by the way, we're expressing surface area in terms of the cross-sectional area, right? Look at the equations. This is where you can just look at the equations. You don't even have to do this procedure, but I'm going to do it just to show that basically you might be able to do this intuitively because all you're doing, you're seeing this, right? You see this and you're like, this is what I have. I just times it by 4, right? You do this intuitively. This is exactly what we do with all of our other things, right? But we write it out because it's easier not to get messed up. All right, so our surface area, we know that our surface area is equal to 4 pi r squared. We also know that r in terms of area is equal to square root of a over pi. Okay, and we write that and we plug that in and we have that is equal to 4 pi square root of a over pi, all that squared. That simplifies to 4 pi times a over pi. The pi's cancel out and you just have 4a. So the surface area in terms of the cross-sectional area, that's just 4a, right? And that's for this one. Don't write this out. This makes no sense to write out. You can just look at it and you see, oh wow, this is 4 pi. Oh my god, I see it right here. All I'm doing is timesing it by 4. But I'm just showing it to you so you can see the procedure behind it. All right, let's look at our final example. This one is expressing volume in terms of the surface area. I'm just going to clean this up over here. I hope you got it all down. Where volume in terms of surface area, right? So what is volume? Volume by itself is 3 over 4 pi r cubed, right? And surface area, how did we rewrite radius in terms of surface area? Well, it's right here. Radius, well, it's right here. Radius is equal to surface area over 4 pi, all of that square rooted, right? And all we're doing, once again, we have our r, and we're just inserting it into the function that has another r, right? It's our common variable here, and we're just rearranging to get it, so we can also use other variables to get our answer needed, right? So what do we do then? Where volume in terms of surface area, that's equal to 3 over 4 pi times surface area over 4 pi to the power 1/2. That's the same thing as the square root to the power of 3. So what our final answer would be is 3 over 4 pi times surface area over 4 pi to the power of 3 over 2. We can't really simplify this anymore. And that's our final formula. And let's think about one last time, what does this really let us do? Well, basically all we're doing right now, before we could only find the area based on the radius, the surface area based on the radius, the volume based on the radius. Now, of course, logically speaking, we could do this a different way. We could find and derive the answers a different way. But what this just lets us do is we can express the volume, for example, in the terms of surface area. So we don't need to know the radius anymore. We can just know the surface area, and we can use this generalized formula. So I hope you understood, and I hope you understand where this concept can be used. And I hope you enjoyed this video, and see you next time.